Thanks. So, hi everyone, my name is Piotr Sarna, and today's presentation is a technical dive on how we used WebAssembly to introduce user-defined functions that are dynamic into libSQL, which is our very own fork of SQLite. I have background in rather low-level and distributed programming, so I was naturally lured towards WebAssembly, especially after I realized it's not only about web development. And now I'm a maintainer of libSQL. So we created libSQL to solve the following problem. We love SQLite, which is a database library, also one of the most widespread software in the world. It's in your phone, it's everywhere. However, it's also developed by a small team of experts, which is super fine on its own, but it's also very hard to contribute to it, especially compared to other open source projects. And SQLite is also very opinionated on what is and what isn't a good use case for it. That's also very fine. Like, opinionated software is great, but there are people, us included, that love the software so much that we actually want to apply it exactly to the use cases it wasn't designed for in the first place. Enter libSQL, which is an open source and open contribution fork of SQLite. And in our development, we focus on making libSQL better suited for edge environments, networking, distributed systems where high concurrency matters, and so on. Just a word of disambiguation. When I say edge, I do not mean the Internet of Things sense, so we're not trying to put a database in your smart fridge or your Bluetooth light bulb yet. But we're just, for now, we're talking about local data centers. Small data centers that might be in your hometown and provide way better latency to your projects. So since we forked, we've already managed to attract some community attention. We gained our first open source contributors, which is kind of why we created the project in the first place. We're working on a few interesting features that allow or make it easier for libSQL to be used in distributed systems, edge computing, serverless, these kinds of environments. And we also slowly drift towards Rust, especially for new code. We actually have strong background in C, which helps with the SQLite code base, but we do believe that Rust is a safer choice and definitely more contributor-friendly as well. Let me start with a very short intro to the architecture. libSQL, just like SQLite, is a database library, so it's just a self-contained library. It's not a distributed system on its own. It's a great building block for one, and it contains everything already. It has its own parser, its own query engine, its own storage layer, and some glue code for running it on the operating system. So you can just embed it right into your application and it works. And now let me explain how user-defined functions fit into the picture and what are the issues that we had and we wanted to overcome with the help of WebAssembly. So user-defined functions already exist in SQLite. The way you use it is, as you would expect, you can have a function, let's say encrypt, which encrypts text, and you can just call it in an SQL statement and get the result that you want. The way it works in SQLite is that you need to actually program the function, for instance, in C or any other language that has proper bindings. All popular languages already have the bindings, so you can pick your language of choice and code the function in it. So what is our issue? Well, there are a few. The first one, you can only register a function by pretty much coding it and then inserting this implementation in your program. And in the distributed system, you don't really want to allow your users to go and change your code, because that's an obvious concern. And then there's also the matter of making sure that your user use the same function. For instance, since it's a distributed system, there might be some users, some clients that use Python and register the function. There might be some clients in Java that also register the function, and it's hard to be sure that it's exactly the same function. It was implemented into two different languages. Maybe it has some different floating point precision, and it may ruin your workloads. So this is also something we would like to change. And finally, user-defined functions, well, as the name suggests, are defined by your users. So running them on your own infrastructure is an obvious security concern. And this is where WebAssembly is kind of an obvious choice due to its sandboxing by design. The existing interface for user-defined functions can be summed up by a few C functions, really. So if you embed SQLite into your project, then you can just write your function, then call this function to register it, and from now on you can use it in your SQL statements. In libSQL, we would like the functions to be dynamically created as well, so that users can actually go and do it through SQL statements. So we introduced, or rather reintroduced maybe, the well-known create function and drop function statements that you can already know from Postgres, MySQL, any other database management system that's out there, with one fundamental difference. Right now, we only support one language for implementing the functions in, and it's not SQL, it's WebAssembly. So let's go over the lifetime of libSQL dynamic user-defined function. When a function is created, we need to take its source code somehow, so the user types in create function and then gives its source code. It can be either binary compiled WASM or WebAssembly text format. And then the next thing we do is store this function in an internal table. The storing is important, first of all, because then the function is immediately available to other users of the database. And secondly, such a definition survives the program restart. You don't need to re-register the function again when you restart your application. And in case somebody provided the source code in WebAssembly text format, we also need to compile it to binary so that we can run it later. Next, a WASM module is instantiated in memory, and with the help of that module, we can register the function in libSQL with the existing interface, so just by calling the C API function that registers the function. And from now on, it can be used as any other user-defined function. Now let's go over how a function gets called. First of all, I'll explain how a regular non-WASM function works, and then point out some differences with the new dynamic WebAssembly functions. So for regular functions, when a user wants to call something, wants to call encrypt, for instance, this function is first looked up in memory in a special data structure that holds all registered functions. And there might be multiple functions with the same name, C++ style. And in that case, we need to find the best fit. Best fit is done simply by comparing what are the parameter types, and the best match is what we should call. And then the function is simply executed. For WebAssembly functions, the flow is a little bit different. It actually starts the same. The function is looked up in the same data structure where non-WebAssembly functions are stored. But then, once we see that this is a WebAssembly function, we need to prepare the runtime a little bit. So we create Wasm store with its memory and a Wasm instance. And then we need to translate types because libSQL has its own set of types and Wasm has its own. So we need to translate the SQL types to WebAssembly to be able to run the WebAssembly function. Then the function is called with the parameters. It returns some value. This value needs to be translated back to the SQL type, and then it can be returned straight to the user. This is a bonus slide, actually. One interesting use case for WebAssembly user-defined functions and libSQL is database triggers. You can do nice things with it. I don't have enough of a time slot to elaborate on it, but if you're interested, feel free to just read the blog post later. And now I'll go through some more implementation details, because the previous slides were a little vague and high level, and now I'll go through how we actually managed to translate types and go from WebAssembly to running something in libSQL. So fortunately for me, the developer, the libSQL type system is really concise. So is the WebAssembly type system if you disregard for a little while all the billions of RFCs that happen every day. So one of them is probably happening right now, getting published. But the basic set is really small. Integers and floating point numbers are trivially representable in both systems. And for text, for strings, and binary blobs, we do need to allocate instance memory. And we have tools to make it easier for the developers. This is the ABI, the binary interface for translating types to and from SQL, libSQL type system, and WebAssembly. Integers and floating points are very trivial to translate, and when we need to pass a text field, so a string or a binary blob, we just need to encode it and send a pointer to it, which is a pointer to the WebAssembly instance memory. And in case of null, we just send a null pointer. Historically, we also allocated memory for nulls, but one of our very considerable external open source contributions from WasmEdge folks was to optimize that and only use a single null pointer. So I wanted to give a shout out for that, because we love open source contributions. So yeah, to continue. Type mapping is not very complicated because it fits on a single slide, but it's easy to get it subtly wrong if you implement it by hand every time. So we decided to make it easier for the developers and create a library. Right now it's in Rust, but we plan to support other languages as well. And with this library, you can write a native Rust function that simply operates on regular Rust types and get it translated to something that we can use straight in WebAssembly, in libSQL. Let's go over an example. This is a regular function written in Rust. It's quite self-explanatory. It has only 3 lines. It takes some arbitrary data, a key, and then uses a crate called magic crypt to encrypt the data with the key, and then returns it. And this is a WebAssembly user-defined function for libSQL that can run inside the database. This is kind of why I love the attributes macros system in Rust, because you can just annotate a function with something and everything happens under the curtain, behind the curtain, and it compiles to something that can be used straight in libSQL. If somebody is not into compiling Rust themselves for any reason, we also created an online playground where you can just type in a Rust function, click a button, and get an SQL create function statement that you can simply copy-paste, put in your libSQL, and then it works. You can use the function from now on. All right, now even more technical details. So far, WebAssembly felt like a perfect fit for our use case for user-defined functions. But especially if you compile from Rust, but not only that, there's one substantial problem, which is bloat. If you're not careful, the binary size of your compiled WebAssembly can get unreasonably huge. You can have a binary that has tens or hundreds of kilobytes, and all it implements is like floating point addition or something. And this wouldn't be an issue if we were running on like supercomputers, but we actually target edge environments, serverless functions, and these have hard limits and constraints with regard to memory. So 1 megabyte per function it's a no-no. But if we manage to make it smaller, then it's a viable solution. So we did explore it quite a bit. Found a few useful tricks how to make the output WebAssembly considerably smaller, and I'll just share the tricks with you now. Some low-hanging fruit first. Disable debug information because it produces megabytes of bloat if you don't need it in your production environment. Set up optimization level S, which stands for size. And by the way, there is also optimization level Z, which stands for aggressive size optimization. But at least for WebAssembly, we figured out with extensive testing that the optimization is so aggressive that it actually produces larger binaries than the regular size optimization. So we stayed with S. Although you can just go and try, maybe it works for you. Next, you might be tempted to just remove the Rust standard library since you're compiling to WebAssembly. And it shaves off lots of the code from the binary, but it also shaves off lots of developer experience. Because in our bindgen library, we want developers to be able to use vector strings, allocate some memory. We want them to use lots of crates, libraries that may depend on the standard library as well. So we figured out a very decent middle ground solution and recompile the standard library with this beautiful free liner. All these options do is turning off and removing panic handlers, because we can decide that we don't want them and our code is panic free. And that actually reduces the binary size quite a lot. Next, the Binarian project has some real goodies, tools that I really like. WasmOpt is a post-compilation optimization tool that also takes an S flag, which stands for size optimization. And it does wonders. You should definitely try it. WasmStrip removes debug symbols, but not only that, also some custom sections. So even if you build without debug symbols, it's worth giving WasmStrip a try and seeing maybe it reduces the size even further. And then when experimenting with binary size, I also stumbled upon Twiggy, which is a size profiler for WebAssembly, and it's also great. I really liked how easy it is to inspect the binary after we compile it and reason about it. So let's go through some examples. Twiggy top gives you a list of top offenders. This example was run on top of a non-optimized binary, and you can see that the top two positions, encrypt and compress, are actually related to the logic that we wanted to implement, so encryption. But the rest is actually not directly related. So this is like a candidate for maybe optimizing it out and removing it from the binary. Twiggy Dominators gives you a dominator tree of the call graph, which sounds complicated, but what it allows you to do is basically see what are the likely candidates of a hot path in your program. This output is actually perfectly reasonable because the binary I inspected only implemented a single function, so this is what should be on the hot path. Twiggy Garbage lets you see if your binary contains some useless data. For instance, that might be debug info or some unreachable code. And normally, WasmOpt and WasmStrip tools should take care of all that. So in that case, Twiggy Garbage wouldn't really report anything, but it's still very nice to incorporate Twiggy Garbage in your continuous integration tools so that you can get regular reports if your Wasm binaries contain some potentially not useful data. And the final minimization slide is a collection of other things that we tried and also helped a little bit. One is WeAlloc, which is an alternative implementation of an allocator, which is a little bit less performant, but also like 10 times smaller than the default. So if you do not allocate heavily, and user-defined functions usually have some simple logic, so they don't allocate very heavily, maybe it's worth it to switch to this simpler allocator, which takes less space. And Wasm Snip is a very nice small tool that lets you cut out a function out of your binary if you're sure that it's not going to be used, and it just replaces it with an unreachable instruction. This is useful if your compiler keeps adding a function to your binary because it cannot prove that it's never used, but you, of course, know better, so you can just snip it out. And this table shows steps from a very naive debug build to the optimized one. And obviously, most of the bloat disappears right after you switch from a debug build with debug symbols to a proper release build. But from there, you can still go 8 times smaller if you apply all the tricks that I mentioned in the previous slides. I bet you can go even further, but we decided that 20 kilo is something that we can live with. So we stopped optimizing right there. If someone knows more tricks, please reach out to me. I'll be very happy to hear about it, and so would be my boss. All right, so now WebAssembly runs on a stack-based virtual machine, like, or maybe stack-ish based, as we've learned in some previous presentations. So in any case, we need such a machine to run our functions on. And right now, we have 2 underlying implementations. One is Wasmtime, and the other is, that came a little bit later, was WasmEdge. WasmEdge. Things we like about Wasmtime is, well, very active open source community, obviously. It's very feature complete. It has good support for async programming, which is important for us because combined with this notion of fuel that I really like, that lets you decide for how long your WebAssembly code should run before it's preempted. This is useful because in a database that has multiple users, you should care about quality of service of some users. So one user's function shouldn't run for too long before checking if other users need something. So this is all very useful for keeping the latency of your database low. Later, we also introduced WasmEdge support. We like it for several reasons. First of all, it was a little bit easier to integrate because it's in C++, and a vast part of libSQL source code is still C, although it's slowly changing. It also has every single feature that we need right now, and it has a very lightweight build that comes, well, without the ahead-of-time compiler, but it has like 1 megabyte in size, which is important in the environments that we target with libSQL. Now let's talk about things we don't have yet, but would love to have in the future. One of them is a nice optimization. So user-defined functions are actually a little bit more complicated than I initially showed on my slides. You can also build user-defined aggregates. You can build window functions, which are a little bit similar. And that already works perfectly fine in libSQL and WebAssembly user-defined functions, but it can be optimized further. What an aggregate is basically a mechanism that runs the same function over and over for each database row and accumulates some partial state. And instead of recreating all the WebAssembly instances to keep the sandboxing on, we could just reuse a single instance and run this function multiple times, and then only return the result once. So it's just a nice optimization possibility. Next, we're using Wasm inside libSQL, but libSQL also compiles to Wasm itself. Right now, the main target is browsers, but we would like to change that too. But in any case, you can compile the whole libSQL code base to WebAssembly. It can run either in memory or even with persistent storage, for instance, local storage in your browser or origin private file system. We also compiled it to Wasm and created an online playground where you can just go to a web page and have a fully fledged SQL engine that runs 100% in your browser. But beyond demo purposes, we also want to target browsers because browsers can be considered something like far edge. It's something that has compute power, like a micro data center. It can also store data, and at the same time, it's very close to the user. So the latency is minimal, and this close proximity means that the user experience is also better if we manage to push the data so close to users. Now, WebAssembly is important for us not only as runtime for user-defined functions, but also as a catalyst for being able to run in the edge environment. So we would very much like to see libSQL run in WebAssembly edge environments like Fermion Spin and Cloudflare Workers and others. So on top of libSQL, we've built SQLD, which is server mode libSQL, capable of speaking Postgres protocol, but also HTTP and WebSockets. And we also have a driver for that, which supports both Spin and Workers right now. So that you can have your own database when developing an application that runs on edge serverless functions that run on WebAssembly. And HTTP is particularly important here because that's the most standard way, sometimes the only way, except for WebSockets, to communicate with the outside world from a hosted WebAssembly instance. And this diagram shows how deployed server-side libSQL could work. You can imagine that you have an application, a web service, and the users wants to register to it, so they click a button. This button click is evaluated on the edge, like Fermion Spin, for instance, and there it's translated to an SQL statement that gets shipped via HTTP to our SQLD cluster, which is simply a distributed database. This database is capable of running WebAssembly user-defined functions as well, so we can run encrypt in there, and then the database server can send the information back to the edge server and then back to the user. And this kind of workflow is exactly what we target because we can both provide a database for the edge, for the data edge, and also let the developers provide their own user-defined functions in WebAssembly. And finally, as I mentioned in the very first slides, we are open contribution, and we already had some, but we would like to have more. The more, the merrier. So if anyone is interested in contributing, then please contact us. We'll be very glad to help you. And that's it. Thanks a lot.
Thank you for the presentation. I think it's very useful, and we are trying to find out how we can achieve these UDFs in our product. So I have a question about, did you do any performance analysis, for example, on a large data set, when you run these UDF functions using Wasm for over, let's say, 1 million records? Did you measure the performance cost? Do you have any analysis on that?
We're not at that stage yet. At first, we just we wanted to make sure that we can run WebAssembly because of sandboxing and the fact that you can code it once and then each user can use them. There's also nothing that we can really compare it to, because we could compare the performance to native functions, but in our model, you can't really let users create the native functions. So we could do benchmarks, but we won't have anything else to compare it really, because WebAssembly was our pretty much only obvious choice.
And also one more question about deploying these functions from the user's perspective. So what's your plan? Like, will it be uploaded dynamically, or will it read from?
Once you have access to sending SQL statements to your database, so if you're a database user, then you can just send over a statement that says create function, then post the function body, and then you can register it. Okay. So that's how it works. So that's why it's dynamic and not kind of statically built like SQLite has.
Thank you.
Okay, I guess we're done. So, thanks everyone, thanks again.